Hi children, this slide presentation explains particle swarm optimization. Particle swarm optimization is a machine learning technique inspired by the flocking nature of birds while searching for the food. Flocking is a coordinated movement or a collective behavior exhibited by birds while searching for the food, or it can be treated as a optimization technique they use while flying long distances during the migratory season. So, in PSO algorithm, it works like a flock of birds. They fly in search of food, where each bird cries at an intensity proportional to the amount of insects or food they find at its current location. At the same time, each bird can perceive the position of the neighboring birds, or it can tell which of the neighboring birds emits the loudest cry, or which of the neighboring locations has highest amount of insects or food. So the chance of finding out a spot with the highest concentration of food depends on the trajectory of birds that combines three directions. One is the current direction of flight, or it keep flying in the same direction. The bird keeps flying in the same direction. Second direction is the return direction, that is it can return to the location where it found the highest concentration of food, or it can remember the location where it found the highest concentration of food. The third direction is the direction towards the neighboring bird that cries the loudest. So the logic that we have explained just now can be represented as a picture. So here you can see 5 particles or agents that collectively move on the search space in search of the global minima point or the global optimum point. So this is actually an one-dimensional function optimization defined over a domain of real values and a single variable one-dimensional function. So each particle or each agent tries to find out the global minima point. So each particle is characterized by its position. Position is important, and as well as its performance. And while optimizing the function, each particle is characterized by value of the particle or the value of that variable that depends on the position of that particular agent, and the value of the function that depends on the performance of that particle. From this slide onwards, we can see the algorithm or the algorithmic steps involved in particle swarm optimization algorithm. So initially, all the agents or particles are randomly distributed on the search space, and they move according to the local information available. And each particle communicates its performance to the neighboring particle. That means its best position. It can communicate its best position to the neighboring particles, as well as it can remember the best position recorded so far. At the same time, it can it can perceive the position of the neighboring particle with the highest performance. So each particle updates its position in this way by adding fractions of 3 displacements. 3 parameters involved in finding out the best position. First one is the fraction of displacement in the same direction it follows by searching for the best position. Second is the fraction of the displacement in the direction toward the position where it records the highest performance so far. That is denoted as the local best position. And the third one is the fraction of displacement in the direction towards the position of the neighbor with the highest performance at that moment. That is the global best position. So these are the equations involved in this algorithm. First is the location updation equation or position updation equation. So the new position xi of t plus 1 means the position of the ith agent at the time t plus 1 is equal to xi of t plus vi of t plus 1. That is the position of the ith particle at the time interval t plus velocity of the ith particle at the time interval t plus 1. So where vi t plus 1 is the new velocity of the particle. So what is this new velocity? The new velocity is equal to a vi of t plus b of xi p minus xi t plus c of xj t minus xi t, where a, b, c are the constants or weights. They can separately control the importance of three terms or the three directions. These three terms are the fractions of three directions involved in velocity updation, where xip minus xit is the difference between the position of the particle where it records the best performance. So that position is xip and its current position, that is xit. And the third term xjt minus xit is the difference between the position of the neighboring particle. Neighboring particle or the neighboring agent is denoted as xj. So it is the difference between the position of the neighboring particle j with the best performance at the moment and the particle's position. So this is the pictorial representation of the logic that we have discussed. So here the update of the position of the particle, that is the particle of interest, is represented as a black disk, which is given by the sum of three directions. First one is its previous direction, second is the direction towards its own best position, and the third is the direction towards the position of its best neighbor. So direction towards the best position so far is represented as a grey disk with black outline, and the global best position is the grey disk without outline. So each of these three directions can be separately weighted by the constants a, b, c, and then furthermore uncertainty can be added to the position of the best on position and the best neighbor position. So whenever a particle records the best performance, its value xi of b will be updated, and the velocity update requires some element of randomness. So some element of randomness need to be added to allow the particles or agents to explore new areas of search space in order to avoid the stagnation in local optima points. So this is obtained by adding a region of uncertainty around the position of the best performance recorded so far and the neighboring particle with the best performance. So that same equation can be rewritten as vi of t plus 1, that is velocity update, is equal to avi of t plus brs xpi minus xit plus crt xjt minus xit. You can see a new variable rs and rt in these two terms, where rs and rt are the random values in the range 0s and 0t, where s and t are some constant values respectively, and these are the terms or these are the variables used to add randomness in this equation, so that we can the agents can explore new areas in the search space to avoid the stagnation or to avoid the local optima point. So the same logic is explained as a picture. So here you can see the area of uncertainty as dotted regions. Two kinds of neighborhoods are explained in this picture. First one is the geographical neighborhood and the second one is the social neighborhood. So in geographical neighborhood, a particle speaks and listens to a small number of particles that are nearby in the space of the function optimization. But in social neighborhood, particles are arranged in some predefined order. Here it is a circle. So during that search, particle can speak and listen to its social neighbors in the dotted area. And the position of the particles in the particle sum optimizations can be updated synchronously or asynchronously, and size of the swarm is actually in the range of 20 to 100, and the neighborhood is approximately, size of the neighborhood is approximately 1/10 of the swarm size, and the constant values a, b, c and the values of values that we have introduced for defining the uncertainty regions, that S and T variables, can be in the range of 0.1 to 1 for low dimensional functions. Now let's see the application area and comparison of particle swarm optimization. Particle swarm optimization can be used in regulation of power plants and the traveling salesperson problems. So when you compare this with other optimization techniques, PSO performs better for optimization of functions of real variables. So it is a good algorithm for optimizing the weights of neural networks. But in the case of multidimensional functions or functions that are defined over discrete or non-Euclidean space, we have to find some method to compute directions and updating the velocities so that the algorithm can converge faster. So this slide is actually a comparison of particle swarm optimization with the evolutionary algorithm. So this performs, or that searches the problem space in parallel with population of candidate solutions. But in evolutionary algorithm, it works like competition among the candidate solution. But in particle swarm optimization, it is the cooperation of agents involved in the algorithm. And the choice of genetic encodings and crossover operators in evolutionary algorithm is equivalent to the choice of position, suitable position, and the velocity updates in particle swarm optimization. So in both cases, it performs well for the real valued function optimization. But when you go for complex and discontinuous problem spaces, where we have to use different mappings and operators, they generate very different results. Both types of algorithms, that is evolutionary algorithms and particle swarm algorithm, both algorithms, they will not perform well. So this slides are prepared based on the textbook of prescribed textbook, Bio-Inspired Artificial Intelligence Theories, Methods and Technologies by Floreno et al. Thank you.